Hello everyone, this is Abhishek Nikam, final year BTech student from Data Science Department at GHRCEM College of Engineering and Management Pune. So I am here today to present my final year BTech project, that is fruit crop disease classification using quantum machine learning. It was developed along with my fellow group members Mr. Aayush Patil and Ms. Sadaf Shaikh under the guidance of Professor Rahul Gawati sir and Mrs. Masira Kulkarni ma'am and our project coordinator Mrs. Rupali Bharte ma'am. So the main motivation behind this work comes from the rapidly growing global population, unpredictable climate patterns, and increasing pressure on agriculture productivity. That is to increase the farmers' yield. Even small infections in fruit crops can spread quickly and drastically reduce yield quality. This affects farmers' income, food supply chains, and overall agriculture economy. Traditionally, disease detection relies on manual inspection by including IoT devices and the farmer needs experts to examine them. So, what our project states that this process is slow, subjective, and often inaccurate, especially in rural areas where experts access is limited. So, by considering the time constraint, we are here with our solution, that is fruit crop disease classification using quantum machine learning, where a farmer can just click plant's leaf photo or the plant's photo and upload it on our platform, so he can see what the disease is or what are the causes for the which are affecting the plant's health. Moving towards the problem statement of our project, so it states that early detection of plant disease is very important to protect crops and ensure food security. Traditional deep learning models like CNNs and MobileNet V2 work very well, but often require large dataset, high computing power, and can overfit on small agricultural datasets. These issues limit their use in real-world farming environments, where resources are low and datasets are small. To overcome these challenges, our project experts a hybrid quantum classical approach for crop disease classification. By combining classical feature abstraction with quantum-inspired models, we aim to build a lightweight, efficient system that can achieve high accuracy on small datasets and demonstrate the potential of quantum machine learning, which is a very trending field nowadays. So we are ensuring or making a model using quantum machine learning for agriculture purpose. So moving towards the next part, that is literature survey. So let's see what were previous studies on quantum machine learning or machine learning in agriculture field and what were their opinions or studies. So first paper is image-based plant disease classification using deep learning by M. Mohante, D. Hobbs, and M. Salate. The findings of these papers included like the potential of deep learning for automated plant disease identification from leaf images. So this also states that the disease can be identified from leaf images. Moving towards the next paper, that is deep neural network based recognition for plant disease by leaf image classification. This study also states that CNN models for plant disease recognition were used using a large dataset of leaf images. The network successfully classified 13 different crop diseases. So it was a multi-classification model developed by M. Salvodik, Arsenic, D. Klubrick, and D. Stefanovic. So our next paper is Deep Learning Models for Plant Disease Detection and Diagnosis by K.P. Ferentinos. The Ferentinos extended earlier CNN-based studies by testing several architectures like AlexNet, VGGs, and ResNet on over 50,000 plant images. It was a huge data set, like 50,000 images are a good quantity. The researcher early achieved over 99% accuracy and highlighted the efficiency of the model. So it was based mainly on CNN models like AlexNet and VGG and ResNet. So basically, he has done a comparative study of different CNN models and achieved 99% accuracy using deep learning models. And the last paper, that is using CNN to identify NPK deficiency in paddy fields and advanced detection methodology. by SM Hooger and MA Wahid. These recent work applied CNNs to detect nutrient NPK deficiencies in rice plants using image analysis. So basically, after checking the disease, we also intend to show the NPK values, like wow, how many nutrients are available in plants, depending on the photo. So this system helps to encourage that feature in our project. The system successfully identified nitrogen, phosphorus, and potassium trace levels through visual leaf system. So this is the system architecture of our final year BTech project. That is hybrid CNN plus quantum machine learning architecture. So here you can see that we first gathered data set from various sources like GitHub, Mendy.com, which included fruits like apple, guava, strawberry, cherry, and also tomato, potato. Yeah, these were the fruits. And so after pre-processing the data set, that is resizing, rescaling, and applying normalization, we applied feature extraction. First, we train our model on basic CNN, then CNN version 2, and then finally quantum QML version, that is with mobile net v2. So after applying feature abstraction, that is training the model in quantum space, applying the quantum concepts to abstract features in three-dimensional and to see the features in more detailed way. So after that phase, here comes the quantum model training. That is with using Qiskit library, and if we got an opportunity to train it on that is real quantum hardware. So it was provided by IBM Quantum Cloud. So after training the model, we integrated it with our Streamlit frontend, and the frontend contains like manual soil input, and also it estimates the AI estimates the chlorophyll and NPK values, and based on that we get a prediction whether the crop is healthy, wilt affected, or nematode. So this is the folder which consists of our entire data set used for our project. So after gathering the whole data set, that is, it was a fully raw, like we needed to classify it in train test well, depending on the subclasses like healthy, wilting, and nematode. We had a split ratio of 70, 15, 15, that is 70% train, 15% test, and 15% validation. So in train, we can see there are three subclasses, that is healthy, nematode, wilting. In healthy, we can see different crops like apple, blueberry, cherry, grape, guava, peach, strawberry. So let's see apple healthy. These are the healthy images of apple. Yeah, you can see these are the healthy images of apple, which are almost 1200 images of apple. And moving towards the nematode infected, so you can see tomato, potato. These are the nematode infected images. Let's see one of those. This is the nematode infected. Actually, this data set was gathered from different sources like Mendeley.com, GitHub, or from other sources, internet sources only. And these are the wilting. In wilting, you can see Gava. These are the wilting images of Gava. Or for grapes, you can see these are the wilted images of grapes. Actually, wilting is the very last stage. Like means the plant is affected with the Mar rog. Yeah, means in Marathi we say Mar rog. So Mar rog we can consider it as a wilting disease. So this was the train, and similarly for the test, and similarly for the validation. So let's move towards the implementation part of our project. So you can see this is the VS Code IDE where I have developed my project. This is the folder named as QML, this which consists of the entire project. I have also shared this project on GitHub. If anybody wants, they can check Nikam Abhi 13 GitHub profile where you can access the same code. So coming to the dataset part, this was the dataset which was previously shown, that is test, train, and validation. This dataset was used for QML model training, that is which allows the RGB values also, RGB images. And for basic CNN models, the process data, that is X-trace, X-train, Y-trace, and Y-train, this was used. And this was the raw data set, that is fruit data set. This was the raw data set, or the data set, this was the raw data set. Okay, so here you can see some of the model, that is base mobile net QNN local.pd. This is the mobile net version of our project. This is the main quantum version of our project. This is the CNN version of our project, that is the basic CNN version 2, and this is the basic CNN version 1. And this is the data splitting script. And I have attached those all models with the front end, that is QCC underscore front end. This front end shows means Streamlit front end was used. So QML training was done using various libraries like Qiskit, Torch, Time. See, the data directory was given. The data directory is equal to dataset underscore to slash train. That is this one. Image size was given 24 by 20, 224 into 224. Number of qubit, that is the simulated QNN input. Batch size, number of epochs, 10 epochs per training were used. And this is the model path, that is the hybrid. Means the after training the model will be saved as hybrid underscore 2, that is this one. Obviously, this can't be loaded. And this is the dataset loading. This is simulating QNN. This is hybrid training. After that is evaluation. Then this is all the main functions which are used to save the best model. Early stopping, I have also included early stopping. So if there are chances of overfitting, the early stop the checkpoint, after checking the checkpoint, the early stopping triggers and the model training breaks. And finally, the best validation accuracy is saved under the name hybrid underscore dot two model. So this is the implementation part behind our project QNN1 hybrid approach. This was the data set, and these are the few model train models by me which are saved here. So this is the interface of our final year project, that is fruit crop disease classification using quantum machine learning. Here you can see in this UI, we have a functionality of uploading a crop image. A farmer or a user can simply drag and drop their leaf images and see the results. Here you can see we have a manual soil in pH input. Like for farmers, we have consider a parameter of soil pH. Using soil pH also, we can determine like how is the plant health. So that's why farmer can manually input the soil pH based on the means now for now it's a manual input, but in future we will integrate it with IoT. So let's test our project. So this is the dataset directory. You can see test. Let's consider a nematode-infected, nematode leaf, and I'm picking a random. Let's drag and drop, and you can see I have uploaded my leaf images, and after uploading, you can see soil and plant health parameters that are AI estimated. So the soil pH was manual, that is 5.7. Soil pH user input 5.7. Chlorophyll content are is AI estimated based upon this image. So the chlorophyll content for this image is 31.26 pad, and the nutrient, that is NPK values, are 11.9, 6.5, 145. These NPK values are estimated from these nutrient heat maps. simulated from leaf color there. So based on those parameters, the system says low chlorophyll plus NPK imbalance and its state possible nematode infection. And the final AI prediction says it is nematode with confidence of 0.78%. So the next farmer advisory steps are the plant may be infected by root node nematodes, leaf may turn pale yellow or drop early. These are the precautionary measures that farmers should follow after the AI detection. Like he should perform actions like keep soil slightly dry, see apply neem cave organic matter in soil, and for next season rotate crops. Or if the condition is very severe, then simply remove the infected plant and burn it. So we can also do it for wilted images. Let's consider another image. Leaf wilting. For wilting, we can do it for grape. Mm, I am choosing an image randomly based. So analyzing image and soil data. Okay, those soil pH was again set for 5.7. The chlorophyll content in this leaf is 28.56, which is again estimated. And the nutrients NPK values are these the based on these nutrient heat maps. Detection that is the AI final prediction is it is a wilting with confidence one means the confidence is almost 100%, and these are the further farmer advisory steps. So this was our final year project, that is hybrid QNN crop assistant, which helps the farmers to detect the what is to detect the disease along with the parameters like soil pH, chlorophyll content, and NPK values, which can be estimated using our system. And these are the further steps like what farmers need to perform. The conclusion and main key takeaways of our project are that we propose a hybrid quantum inspired approach for crop disease detection. The conclusion and the key takeaways of our project are that we propose a hybrid quantum inspired approach for crop disease detection, leveraging the strength of both quantum machine learning and CNN. Our result demonstrate that the quantum inspired model outperforms traditional CNN models in terms of accuracy and efficiency, which can be seen that our model, that is QNN plus mobile net v2, achieved accuracy of 99.8%, whereas the basic mobile net v2 achieved accuracy of 96%, and the basic CNN version 1 and CNN version 2 achieved 80% and 94% accuracy. So it states that quantum uh, quantum machine learning is nowadays in very boom, and if possible, if we had the main hardware, that is quantum hardware, we can reduce the training time and also use RGB values or RGB images directly for training our model instead of grayscaling and converting them into black and white images. So these are the some of the advantages of our project, which can be also integrated with IoT devices or the hyperspectral images, that is using the satellite navigation. We can also detect the plant health in a farmer's field. Means by using the hyperspectral images, we can simply see the chlorophyll values, NPK values in a particular region of a farm, and the farmer can detect in which part the plant is affected, and thus he can save a lot of time. Thank you.